Okay, I alluded to this problem in the last video and said I might put it on a quiz. Then I looked at your textbook and saw that they actually worked it out for you in there. So I thought, okay, I'll turn it into a video. Okay. I want to take a look at changing to spherical coordinates. But rather than thinking of that as let's just chop things up into spherical wedges, I want to think of that as a transformation of three space, or a change of variables. Okay. So what I've drawn here is the rho, theta, phi coordinate system. So here, rho and theta and phi have nothing to do with spherical coordinates. They are rectangular coordinates. Rho is indicating how far forward we're coming. Theta, how far left or right. Phi, how far up or down. And I've drawn in this rectangular box here. Now it's meant to be an infinite box that extends infinitely far forward. But the other boundaries are actually meant to be there. So I've restricted phi to be between 0 and pi, just like we do for spherical coordinates. I have restricted rho to be non-negative. So the front is a false front, but the back is right there at rho equals 0. And I know in spherical coordinates I don't actually restrict theta, but for any one problem, theta isn't going to vary over an interval of length more than 2 pi. So for any one problem, theta is going to be in some interval of length 2 pi. Here I've restricted things to be between 0 and 2 pi. I could just as easily have gone from negative pi to pi, or from 2 pi to 4 pi. Any of those would work. Okay. And then I've given you this transformation that writes x as what I'm used to thinking of x in spherical coordinates. Rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. This transformation will map an infinite box like this to all of three space. Okay. All right. Now, the transformation isn't quite one-to-one, because I know if rho is 0, that's going to put me at the origin, and theta and phi could be whatever we wanted. So the entire line where rho is equal to 0, or the entire, actually plane where rho is equal to 0, all maps to this point. If phi is 0 or phi is pi, so that puts me on the z-axis, rho would have to be fixed so that I land at the right point on the z-axis, but theta could be whatever we wanted. So it's not quite one-to-one because points on the z-axis do not have unique names in spherical coordinates. I'm just going to tell you that that's an ignorable problem. This is close enough to one-to-one that using the Jacobian to keep track of our scaling factor does work. Okay. So I know that if I had a triple integral over some region R of f of xyz dv in the xyz plane, I know that should be the triple integral. I'm just going to write appropriate limits here because I'm going to write this one as an iterated integral. That would be f of t of rho, theta, and phi. So that would just express x, y, and z in terms of rho, theta, and phi. Scaling factor, d rho, d phi, d theta. And I know what that scaling factor should be, because I know when I switch to spherical coordinates, I'm supposed to get rho squared sine phi. But I also know that that's supposed to be the absolute value of the Jacobian. So I'm going to calculate the absolute value of that Jacobian and prove that it actually is rho squared sine phi. Okay. Now, if you want to at this point pause the video and work this out, fabulous. I will just remind you, don't forget to take the absolute value of the Jacobian once you've actually calculated the Jacobian. Okay. If you want to work through it with me, that's fine, but otherwise, pause. See you soon. Welcome back. Okay. So if I just find the Jacobian, we'll take the absolute value at the end. The Jacobian, I know, is going to be the determinant of this matrix. Partial x partial rho, partial x partial theta, partial x partial phi. Reminder, we're mapping two x, y, z, so x, y, and z go to determine the rows. Okay, that means rho, theta, and phi are the columns. Also, x, y, and z are the outputs, and rho, theta, and phi are the inputs All my partials are output over input. Okay, so then we'll have partial y partial rho, partial y partial theta, partial y partial phi, partial z partial rho, partial z partial theta, partial z partial phi. Okay, so let's write out what these are. The partial of x with respect to rho is just sine phi cosine theta. The partial of x with respect to theta is going to be negative rho sine phi sine theta. And the partial of x with respect to phi is going to be rho cosine phi cosine theta. Partial of y with respect to rho is sine phi sine theta. Partial of y with respect to theta is rho sine phi cosine theta. Partial of y with respect to phi is rho cosine phi sine theta. Partial of z with respect to rho is cosine of phi. No theta, so the partial with respect to theta is 0. And then the partial with respect to phi is negative rho sine phi. Okay, I need more space. So now, I'm calculating, let's just keep track. I'm calculating the Jacobian. Going to have to remember to take the absolute value when I'm done. Okay. Now, if you remember when we talked about 3 by 3 determinants, we usually expanded on the first row, but I mentioned you could expand on any row or column. I'm going to expand on row 3 because I really like having that 0 there. So I just want to remember the rule. When I expand on the first row, I keep the sign of the first term, change the sign of the second, keep the sign of the third. Just keeps alternating. So the next row goes minus plus minus, this row goes plus minus plus. Okay. So I'm going to keep the sign of my first term, change the sign of the middle, keep the sign of the third. Okay, so I'm going to get cosine of phi times the determinant of this 2 by 2 matrix right here. So negative rho sine phi sine theta, rho cosine phi cosine theta, rho sine phi cosine theta, rho cosine phi sine theta. Minus 0, I like that middle term, plus negative rho sine phi times the determinant of this 2 by 2 matrix. So that's sine phi cosine theta, negative rho sine phi sine theta, sine phi sine theta, rho sine phi cosine theta. All right. So that's going to give me cosine of phi times this diagonal product is negative rho squared sine phi cosine phi times sine squared theta minus this diagonal product is rho squared sine phi cosine phi times cosine squared theta. Then I've got a minus rho sine phi times this diagonal product is going to be rho sine squared phi cosine squared theta minus a negative, so plus rho sine squared phi, sorry there was a phi in there, times sine squared theta. Now, looks messy, but notice from these terms I can factor out a negative rho squared sine phi cosine phi. So if I do that, I'm going to have a negative rho squared sine phi cosine squared phi, because I'm factoring out one cosine and there's already one out there. And then what's left that's multiplied by is just sine squared theta plus, because I factored out the negative, cosine squared theta, and that's just 1. Now here, I can factor out a rho sine squared phi. So I'm going to have a minus rho squared sine cubed phi times what's left is cosine squared theta plus sine squared theta, and that's also just 1. So this long thing is starting to collapse down. So we get negative rho squared sine phi cosine squared theta I'm sorry, that was supposed to be cosine squared phi. My bad. Remember, that was from the cosine phi that we factored out and the cosine phi that was already there. Okay. So that should be a cosine squared phi, not a cosine squared theta. Minus rho squared sine cubed phi. Well, I'm going to factor some stuff out. So I'm going to factor out a negative rho squared sine phi, and what's left then is cosine squared phi plus, because I factored out the negative, no, I'm sorry, that was sine cubed phi. Oh my goodness. I factored out one of those signs, got 2 of them left. That's just 1. So we've got negative rho squared sine phi. At which point our hearts might sink because we know the scaling factor is supposed to be rho squared sine phi. But this was just the Jacobian. The scaling factor is the absolute value of the Jacobian. So that's going to be the absolute value of negative rho squared sine phi. Now, the absolute value kills the negative sign. Rho squared, of course, is just positive, or at least non-negative. So then I have to look at phi. But the absolute value of sine phi in this case is just sine phi, and that's because phi is restricted to take on values between 0 and pi so that its sign is positive. So our scaling factor is indeed rho squared sine phi.